So we've been looking at comparing populations. We've looked at difference in proportions, difference in means, and now we want to look at differences in paired data, and I'll show you what I mean by that. So the best way to illustrate this is by an example and see why this is really different than what we've done already. So imagine we were testing a new race car tire design. And what we're going to do to test it versus the old design is take a bunch of drivers and have them go around a track with both, first the old tire, then the new, and compare their time on 10 laps. So we take 30 pro drivers, and they do 10 laps in old tires and 10 laps in new tires. So what I mean by old and new is the old design and the new design. So what we would have is data where we might have the driver 1, driver 2, driver 3, 4, and so on. And then we would have their time on the old tire. Let's say driver 1, say it was 280.1 seconds. Driver 2 was 271.5 seconds, and so on. We would have times for all 30 drivers here. And then we would time them on 10 laps going around, same car, only change is the tires. Keeping the same driver is the key here. So 276, let's say on the new tires, driver 1 does 276.5 seconds. Driver 2, 269.8 seconds, and so on. So we'd have these pairs of times for old tire and new tire for each driver. And we could look at, say, the difference here. And I won't put that up just yet because we'll go to the computer to look at the differences. But the reason this is different than what we did before is we don't want to treat these as two independent populations. It's not like these numbers have nothing to do with these numbers, right? This particular value really goes with this value because they are from the same driver, right? That's driver 1's times, driver 2 times. So we don't want to just average these times and average these times without keeping the connection. Hence the idea of what we call paired design or matched pair data we have. Each one of these has a natural pairing. So in each one of these pairs, we will look at old minus new. So just for example, old minus new, that's an improvement of 3.6 seconds in the time, right? It lowered his time by 3.6 seconds. The next driver, 1.7 seconds, and so on. And so it may seem like it doesn't make a difference. Why not just take these times, treat that as one sample? We already know how to do a difference in means. We could just take this mean and see if there's a statistical difference there. But I want to move over to the data and show you why you really don't want to do that and why it's really more appropriate to treat this as matched pairs. So let's take a look at the data. So here's our data I've got that we started on over there. There's the drivers. We've got our 30 drivers, their time in the old tire, time in the new tire, and then computed the differences. Now you'll notice you could take the, for example, old tire information and calculate the mean, which would be 274.583 repeating. You could look at the new tire info and compute the mean, 273.59. And you could take the difference in those two, and you would get 0.993 repeating. Or you could take the mean of these differences. Well, mathematically, there's no difference. You would get the same thing. So at first glance, it might seem like it's really immaterial to treat them as matched pairs. Why not just take this mean minus this mean and test that difference, instead of taking all the individual differences and taking the average of those? Well, where the difference comes in is look at the standard deviation. If we just treated this as a sample from an independent population, these values on the old tire have a standard deviation of 12 seconds. On the new tire, there's a standard deviation of 12 seconds. Those standard deviations would go into computing our sampling distribution's variability. And they're quite large compared to the standard deviation of the differences is actually quite small. Now, what does that mean? Why are these large while this is small? Well, there's a lot of variation in these times here under old tire or new tire. But that has nothing to do with the tire. That's the differences in the drivers, right? These drivers make it around the track in different times. So there's variability due to the drivers, but they're very consistent within each driver, right? So when we look at the difference, all that variability in drivers goes away, because now we're just looking at the difference in those matched pairs, and there is very little variability when we look at those differences. That's going to affect, on the theory side of things, the variability in what our sampling would be. So you would get very different p-values if you treated this separately as if you treated it as matched pairs. And so that's what we're going to look at coming up. We'll look at how to simulate a test on, is this difference here significant? And we can compare it to the two approaches. What happens if you treat it as two separate populations, or what happens if you treat it as matched pairs?